Either way, it shows these animals were far more behaviorally complex than we might expect from something called a giant sloth. Here's another fascinating discovery about ground sloths. In Ecuador, at a site called Tanque Loma, paleontologists found the remains of at least 22 Eremotherium sloths of various ages, all in the same location. They likely died during a drought, getting trapped in a shrinking watering hole. But the cool part is what this tells us about their behavior. They were congregating at watering holes, which means they were social animals living in groups. And they were probably wallowing in the water to escape heat and insects, similar to how hippos and rhinos behave today. Wait, wallowing sloths? It's incredible to think that even during the Ice Age, not every place was frozen all the time. Tropical and subtropical regions still had warm seasons. The climate was cooler and drier than today, but the equatorial regions weren't covered in ice sheets. It meant animals still needed ways to deal with heat. In South America, ground sloths used strategies that large African mammals still use today. The Ice Age wasn't a uniformly frozen world. And speaking of surviving the cold, let's return to mammoths. The ones preserved in Siberian permafrost have given us such an incredible amount of information. Some have even had their last meals preserved in their stomachs. When scientists examined this material, they found grasses, sedges, herbs, flowers, and mosses. It painted a picture of exactly what the mammoth steppe ecosystem was like and what plants were available. But it gets even better. We've extracted DNA from these frozen specimens and sequenced entire mammoth genomes. The genetic analysis revealed some truly wild adaptations. Mammoths had variations of hemoglobin, the protein that carries oxygen in the blood, that functioned better at cold temperatures. Normal hemoglobin doesn't release oxygen as efficiently when it's cold, which would be a problem for an animal living in freezing conditions. Mammoth hemoglobin had mutations that compensated for this, allowing their blood to deliver oxygen effectively even when their body tissues were cold. That's hardcore molecular adaptation to cold environments. We've also found that mammoths had genes for small ears, sparse sweat glands, and improved fat storage, all coded in their DNA. Evolution didn't just change their external appearance. It rewired their physiology at the genetic level. And here's something poignant. The last mammoths to ever exist lived on Wrangel Island in the Arctic Ocean. This island was cut off from the mainland when sea levels rose after the ice sheets melted. A population of around 500 to 1,000 mammoths survived there in isolation until about 4,000 years ago. That's after the pyramids of Giza were built. It's during the Bronze Age. Mammoths and ancient civilizations overlapped in time. The last of these giants were still walking around on a remote Arctic island while humans in Egypt were building monuments and developing writing. And then they went extinct, probably due to a combination of inbreeding, habitat degradation on their small island, and possibly climate change or human arrival. It was the end of an evolutionary line that had lasted for millions of years. Woolly rhinoceroses are another species we know a lot about from frozen specimens. Like mammoths, they had thick woolly coats and were built for the cold. But their behavior was probably different, based on their tooth wear and the isotopes in their bones. Scientists think woolly rhinos were more selective feeders than mammoths, while mammoths were bulk grazers, eating lots of whatever vegetation was available. Woolly rhinos seemed pickier, probably using their horns to dig through snow to find specific plants they preferred. The giant deer, Megalochorus, had antlers that were absolutely insane. The largest specimens had antlers spanning over 3.5 meters from tip to tip. That's wider than a car. These antlers could weigh up to 40 kilograms. Carrying that much weight on your head takes serious neck and shoulder muscles. Scientists think these massive antlers were primarily for display and competition between males, similar to how modern deer use their antlers. During mating season, males would show off their antlers to females and use them in battles with rival males. The bigger your antlers, the more impressive you looked. But those antlers came with a cost. Growing them required huge amounts of calcium and energy, and carrying them around was energetically expensive. Only the healthiest, best-fed males could support truly enormous antlers. Cave bears are interesting because, despite their name and their size, they were mostly herbivorous. Isotope analysis of their bones shows they ate primarily plants. They were built like grizzly bears but acted more like giant pandas. They hibernated in caves during winter, which is where we find most of their fossils. Some caves in Europe have thousands of cave bear bones, representing hundreds or thousands of individuals that hibernated there over millennia. And cave bears went extinct earlier than many other megafauna, around 27,000 to 24,000 years ago, well before the end of the last glacial period. The reasons aren't entirely clear, but it might have been related to competition with humans for cave space, climate changes affecting their food supply, or a combination of factors. Glyptodons are still blowing my mind the more I learn about them. Recent studies of their skeletal structure and muscle attachment points suggest they were capable of some surprising behaviors. They might have been able to rear up, as we mentioned, but they also show adaptations for powerful digging, similar to what we see in modern armadillos, but scaled up massively. So, these armored giants might have dug burrows like their ground sloth contemporaries. Imagine tunnels big enough for a Volkswagen Beetle to drive through, created by armored animals with spiky tails. The Ice Age was wild. The predators of the Ice Age were just as specialized as the herbivores. Saber-toothed cats didn't just have those impressive fangs for show. Biomechanical studies of their skulls show they had relatively weak bite forces compared to modern big cats, but their neck muscles were incredibly powerful. The hunting strategy was probably to use their strong forelimbs to wrestle prey down, then use their neck muscles to drive those saber teeth deep into the prey's throat or belly with precision. It wasn't about crushing force, it was about precision. The dire wolf. I've spent years studying its fossil record. What strikes me most is how many of them died in the La Brea tar pits. Thousands, trapped over tens of thousands of years, stuck in that asphalt while trying to scavenge. Those fossils tell a story of survival and even, perhaps, of compassion. Many specimens show broken teeth, healed fractures, and signs of arthritis, especially in the older ones. To me, this suggests they lived in social groups, caring for the injured and elderly. A wolf with a broken leg simply couldn't hunt alone. If the pack shared food, though, it could survive. It's compelling evidence that dire wolves had complex social structures much like modern wolves. Giant short-faced bears, though, remain more mysterious. Were they primarily predators or scavengers? The evidence is mixed, you see. Their long legs suggest they could cover long distances efficiently, which would be useful for scavenging. But their powerful jaws and teeth could certainly kill prey. Perhaps they were opportunistic, hunting when possible, scavenging when available. Their sheer size, potentially the largest mammalian land predator ever, suggests they could intimidate smaller predators and steal their kills. I imagine a pack of dire wolves bringing down a bison, only to have a giant short-faced bear show up and chase them off, claiming the carcass. One of the coolest things about Ice Age ecosystems is that we have evidence of how they functioned from an unusual source: ancient DNA in sediments. Even without bones or visible fossils, DNA from animals can be preserved in frozen soil. Scientists have developed techniques to extract and identify this environmental DNA, and it's revealed which species were present in different places at different times. It's filled in gaps in the fossil record and shown us that Ice Age ecosystems were even more diverse than we realized. We now know horses were present in areas where we don't have horse fossils, simply because we found horse DNA in the soil. We've identified plants that grew in certain regions by finding their pollen and DNA. We can even tell what the climate was like by looking at which species of plants and insects were present. It's like reading an ancient ecological record written in genetic code. Humans were there, observing and interacting with all of this megafauna, and they left records of what they saw. Cave art from sites like Lascaux in France and Chauvet Cave shows remarkably accurate depictions of Ice Age animals. The artists painted mammoths, woolly rhinos, bison, horses, cave lions, and more. And these paintings aren't crude stick figures. They're sophisticated artworks showing animals in motion, using the natural contours of the cave walls to create three-dimensional effects. The artists clearly spent a lot of time observing these animals to capture them so accurately. Some cave paintings even show details like fur patterns, seasonal coat changes, and behavioral poses. There's a famous painting of a woolly rhino that clearly shows its thick fur and the way it held its head. There are paintings of mammoths that show their characteristic domed heads and long tusks. These artworks are our direct visual record of what Ice Age megafauna looked like, created by people who saw them alive. Humans also left behind butchered animal bones, showing clear-cut marks from stone tools, mammoth bones with spear points embedded in them, campsites with hearths surrounded by the remains of horses, bison, and reindeer. The archaeological record proves that humans hunted megafauna and relied on them for food, materials for tools and clothing, and fat for fuel. Mammoth ivory was carved into art objects and tools. Hides were used for clothing and shelter. Bones were used to build dwelling structures in areas with scarce wood. Every part of these animals was utilized. But humans weren't just passive observers or simple hunters. There's evidence that humans might have used fire to manage landscapes, creating and maintaining the open grasslands that megafauna depended on. By burning vegetation regularly, humans could prevent forests from encroaching on grasslands, keeping habitats open for the large herbivores they hunted. This kind of ecosystem engineering might have actually helped support megafauna populations in some regions. The relationship between humans and megafauna was complex, not just predator and prey. The 100,000-year cycle had created this entire world. The cold phase of the cycle produced these unique ecosystems and drove the evolution of specialized megafauna adapted to frozen conditions. For hundreds of thousands of years, the pattern repeated. Ice sheets advanced. Megafauna thrived. Ice sheets retreated. Forests expanded. Ice sheets advanced again. Life adapted to this rhythm. But then, about 19,000 years ago, the cycle began shifting toward warming again, and this time, something was different. This time, humans had spread across most of the world, developed sophisticated hunting technologies, and existed in larger numbers than ever before. This time, when the climate started changing and the ice began to melt, the megafauna wouldn't just adapt and wait for the cycle to swing back to cold like they had for hundreds of thousands of years. This time, most of them were going to disappear forever, and we're still debating exactly why. Around 19,000 years ago, the 100,000-year cycle reached a turning point. The orbital configuration shifted into a pattern that favored warming. Northern Hemisphere summers started getting stronger, receiving more solar radiation. And when that happens, winter snow starts melting more completely each summer. Ice sheets stop growing and begin their long retreat. The transition from glacial to interglacial conditions was underway, but deglaciation isn't a smooth process, it's messy. It happens in fits and starts. There are sudden collapses and temporary reversals, and periods of rapid change that people living at the time would have noticed within their own lifetimes. This very messiness is what makes understanding the extinction of the megafauna so incredibly complicated. The first major pulse of melting occurred around 19,000 years ago and continued for several millennia. As the ice sheets melted, sea levels began to rise, pouring water back into the oceans. During one period, around 14,600 years ago, called Meltwater Pulse 1A, sea levels rose by roughly 20 meters in less than 500 years. Now, 20 meters may not sound like much, but that's enough to flood vast coastal areas, submerge land bridges, and utterly transform coastlines. All that water had to come from somewhere, of course. It came from collapsing sections of the great ice sheets. The Laurentide ice sheet, that massive dome of ice covering Canada, began breaking apart. The Fennoscandian ice sheet in Europe did the same. As they melted, they left behind a landscape that had been compressed under kilometers of ice for thousands of years. The land was scraped clean, covered in glacial till, dotted with lakes formed in depressions carved by ice. I imagine it must have been a raw, bare landscape at first, slowly being colonized by plants as the climate warmed. But the warming wasn't steady. There were dramatic interruptions, the most famous being the Younger Dryas event. By around 14,700 years ago, the world had been warming for thousands of years. Ice sheets were in retreat. Things seemed to be heading toward interglacial conditions. Then suddenly, temperatures crashed. In Greenland, temperatures dropped by about 15 degrees Celsius in just a few decades, possibly even faster. Some evidence suggests it could have happened in as little as 10 to 20 years. The North Atlantic region was plunged back into near glacial conditions that lasted over 1,000 years. The leading theory involves a catastrophic flood. As the Laurentide ice sheet melted, water pooled up behind it, forming enormous glacial lakes. The largest was Glacial Lake Agassiz, which was bigger than all of the modern Great Lakes combined. This lake was dammed in by the ice sheet itself, and when that ice dam failed, and geological evidence suggests it did multiple times, absolutely stupendous amounts of fresh water flooded into the ocean in a geologically instant time frame. We're talking about enough water to raise global sea levels by several meters, all released in months to years. This massive freshwater dump disrupted ocean circulation in the North Atlantic. There's this ocean circulation pattern called the Atlantic Meridional Overturning Circulation, or AMOC. It's basically a conveyor belt where warm surface water flows north, cools down near Greenland, becomes dense and sinks, then flows south at depth. This circulation transports enormous amounts of heat from the tropics to the northern hemisphere. But fresh water is less dense than salt water. When you dump a huge amount of fresh water into the North Atlantic, it floats on top and prevents the normal sinking of cold, dense water. This can slow down or shut down the AMOC, and when the AMOC stops, the northern hemisphere stops receiving that massive heat transport from the tropics. Temperatures crash, and you're back to near glacial conditions. The Younger Dryas had effects far beyond the North Atlantic. Climate patterns shifted across the globe. Some regions got drier, others wetter. Temperatures changed, and this had huge impacts on ecosystems and the animals living in them. For megafauna that were already stressed by changing habitats as the climate warmed and forests expanded, the Younger Dryas cold snap might have provided a temporary reprieve, but it also added instability to an already unstable situation. It had major impacts on human societies, too. In the Middle East, this is right around the time agriculture first developed. Some scientists think the climate stress of the Younger Dryas might have pushed hunter-gatherer groups to start deliberately cultivating plants as a way to end food security when wild resources became unreliable. If that's true, then this climate event, triggered by the 100,000-year cycle transitioning from glacial to interglacial, literally changed the course of human history, setting us on the path to farming, settled civilizations, and everything that followed. But eventually, around 11,700 years ago, the Younger Dryas ended, and it ended just as abruptly as it started. Temperatures spiked upward again. In some regions, temperatures rose by 10 degrees Celsius or more in just a decade or two. That's mind-bogglingly fast for natural climate change. The AMOC kicked back into gear. Heat flooded northward again. Ice sheets resumed their collapse, and this time there was no going back. The transition to full interglacial conditions was complete. We call this the beginning of the Holocene, our current geological epoch, and it marks the end of the last glacial period. For the megafauna, this was catastrophic. They had evolved over hundreds of thousands of years to thrive in cold, open grassland environments. But as the Holocene began, those environments were disappearing. The mammoth steppe, that unique ecosystem of cold grassland that had supported enormous populations of large herbivores, was transforming. Forests were expanding, grasslands were shrinking, the climate was getting wetter and warmer. For animals adapted to cold and dry conditions, this was a crisis, and the extinctions came fast. In North America, most megafauna disappeared between about 13,000 and 11,000 years ago. Mammoths, mastodons, horses, camels, giant ground sloths, saber-toothed cats, dire wolves, giant short-faced bears, all gone within a few thousand years. 70 to 80% of large mammal species just vanished. I find that number staggering. It was devastating, this quaternary extinction event. Across the world, the megafauna just vanished. In Europe, we saw similar losses, though the timing shifted depending on the species. Woolly mammoths disappeared from most places, clinging to existence only in isolated spots like Wrangler Island. Woolly rhinos, cave lions, giant deer, gone. The megafauna that had dominated Europe during the Ice Age were either gone or severely reduced in number. South America suffered just as badly. Giant ground sloths, all the different species that had evolved there, extinct. Glyptodonts, gone. Native horses and camels, extinct. Toxodons, macrochenia, giant armadillos, all gone. The extinction wave swept through the Americas like wildfire. Australia had already lost most of its megafauna earlier, between 50 and 40,000 years ago. Giant wombats, enormous kangaroos, massive flightless birds, even a marsupial lion, all disappeared. The timing in Australia, though, lines up more closely with the arrival of humans than with the last deglaciation. This adds another piece to the puzzle. What killed them? This question has been debated for decades, and honestly, it's still not completely settled. There are two main schools of thought: the climate change hypothesis and the human hunting hypothesis. The truth is probably a combination of both, with the relative importance of each varying by region and species. The climate change hypothesis argues that the rapid warming and ecosystem transformation was more than these animals could handle. Megafauna had evolved for cold, open habitats. When those habitats disappeared in just a few thousand years, they couldn't adapt quickly enough. As forests expanded and grasslands shrank, megafauna populations became fragmented into smaller and smaller pockets of suitable habitat. Small isolated populations are vulnerable to inbreeding, disease, and random environmental fluctuations. This creates an extinction vortex, where declining populations face multiple threats that compound each other, and recovery becomes impossible. There's good evidence for climate being a major factor. The extinctions happened during a period of incredibly rapid climate change. Species adapted to cold climates, like woolly mammoths and woolly rhinos, went extinct, while species adapted to forests or warmer climates generally survived. This pattern suggests climate played a big role. Also, megafauna had survived previous deglaciations. The 100,000-year cycle means there were multiple transitions from glacial to interglacial conditions over the past few million years. If megafauna survived those, why not this one? That's where the human hunting hypothesis comes in. Modern humans had spread across most of the world by the end of the last ice age. And humans are incredibly effective hunters, especially with the technological innovations that developed during this period. Atlatls, spear throwers that dramatically extend your range and power. Sophisticated hunting strategies involving coordinated groups, and later, bows and arrows. Human populations were growing and spreading into new territories. And critically, many megafauna had little or no evolutionary experience with human hunters when humans first arrived in the Americas or Australia. The local megafauna hadn't evolved fear responses to these two-legged predators. They were naive prey. Modern examples show this pattern. When humans first reached oceanic islands with no previous human presence, the native birds and mammals often showed no fear and were easily hunted to extinction within decades or centuries. The same might have happened with Ice Age Megafauna. They simply didn't recognize humans as threats until it was too late. And here's the thing about hunting megafauna. You don't need to hunt intensively to drive them extinct. These animals have slow reproductive rates. A female mammoth might have a calf every 5 years. Mammoths don't reach sexual maturity until they're teens. If you kill even a few individuals per year from a population, especially females of reproductive age, you can drive the population into decline. Mathematical models show that even very low-intensity hunting, killing just a few percent of the population per year, can drive large-bodied animals extinct over centuries to millennia. And we know humans hunted megafauna. We've found butchered mammoth bones at human sites, spear points embedded in mammoth ribs, kill sites where multiple animals were driven off cliffs or into traps and then butchered, cave paintings showing hunting scenes. The evidence is undeniable that humans hunted these animals. The question is whether hunting alone could cause extinctions, or whether it was just the final straw for populations already struggling with climate change. The timing is really suspicious in many regions. In North America, the extinctions coincide almost exactly with the expansion of Clovis culture, a group of humans with particularly effective hunting technology. Clovis points, these distinctive spear points, are found at sites with butchered mammoth remains. Within a few thousand years of Clovis people spreading across North America, the megafauna were gone. That's awfully coincidental timing. A study of the Anzac child, the only known Clovis individual, provides some interesting evidence. This was an 18-month-old child buried about 12,700 years ago in Montana. Scientists analyzed isotopes from the bones to reconstruct the diet of the child's mother, and they found that mammoth contributed around 40% of the maternal protein diet, similar to the diet of specialized mammoth predators like scimitar cats. This suggests Clovis people were heavily targeting mammoths, possibly as specialized mammoth hunters. But we need to be careful not to overinterpret. The Anzac child is one individual. We can't say all Clovis people had the same diet or hunting for the disappearance of the Ice Age giants. I keep thinking about how some species vanished quickly while others held on. Mammoths, for instance, survived on Wrangler Island until about 4,000 years ago, long after their mainland cousins were gone. Cave bears disappeared even earlier, and it's a puzzle why some species, like bison, endured heavy hunting while others didn't. What's clear to me is that it wasn't just one thing. Climate change put immense stress on these megafauna populations, shrinking their habitats and making food scarce. Then came humans, and our hunting tipped the balance, preventing those struggling populations from ever bouncing back. A perfect storm, really, that most couldn't weather, and perhaps there were other factors, subtle and indirect. Humans used fire to shape the land, changing the vegetation. The loss of mammoths and other large herbivores transformed ecosystems. Grasslands turned into forests, making life even harder for any remaining megafauna. It's also interconnected, a cascade of effects. For hundreds of thousands of years, these megafauna had adapted to the rhythm of 100,000-year cycles, thriving in the cold, retreating to safe havens in the warm. But this time, something was different. This time, there were humans, with sophisticated tools and growing numbers. The combination of rapid climate change and human press proved too much, and within a few thousand years, the world of Ice Age giants was gone. But the story of the humans who lived through those cycles is just as fascinating, and when I say humans, I'm not just talking about us. Neanderthals were already here, well established, and they deserve far more credit than they often receive. They were the original Ice Age survivors, evolving in Europe and parts of Asia hundreds of thousands of years before our ancestors even left Africa. They weren't some primitive dead end. They were intelligent, sophisticated humans, remarkably adapted to glacial conditions. Their very bodies were adaptations. They were short and stocky, with barrel chests and thick bones. An average male might have been only about 160 centimeters tall, but they were incredibly strong. It was all about conserving heat. Shorter, stockier bodies lose less heat, a principle we see repeated in the megafauna themselves. And their faces, with those large noses and wide nasal passages, were like built-in air conditioners, warming and humidifying the frigid air before it reached their lungs. But it wasn't just physical. Neanderthals possessed a sophisticated culture and technology. They crafted complex stone tools using the levallois technique, requiring planning and a mental image of the finished tool. They made wooden spears, carefully shaped and balanced, with fire-hardened tips, and they hunted big, dangerous game, bison, reindeer, even woolly rhinos and mammoths. These weren't scavenged carcasses. The bones bear clear butchery marks. They also used fire extensively, not just for warmth and cooking, but for creating complex adhesives. The birch bark tar they used to attach stone points to wooden handles required a multi-step process and technical knowledge. Perhaps most impressive, Neanderthals engaged in symbolic culture. They created ornamental objects, pierced shells, eagle talons worn as jewelry. They used pigments, possibly for body painting or decorating objects. And they buried their dead, sometimes with grave goods or in deliberate postures. That burial at Shanidar Cave in Iraq, where there's evidence suggesting flowers were placed in the grave, I find it incredibly moving. I often find myself pondering the fate of the Neanderthals. They were so much like us, even burying their dead with intention, suggesting a deep understanding of mortality and ritual. That, to me, is profoundly human. They even left art behind, abstract geometric patterns and hand stencils in Spanish caves, dating back to a time when they were the sole inhabitants of the region. These are some of the earliest examples of cave art we know of, pushing back the timeline of when symbolic thought emerged. And it wasn't just an isolated incident. Similar markings have been discovered at multiple sites, hinting at a widespread Neanderthal culture. So, what happened to them? Why did they disappear when they seemed so capable? That's a question that keeps many of us in paleoanthropology up at night. The last Neanderthals vanished around 40,000 years ago, just as modern humans were spreading across Europe from Africa and the Middle East. The timing is undeniably suspicious. Did we outcompete them, absorb them through interbreeding, or did we simply drive them to extinction? The genetic evidence is clear. Neanderthals and modern humans did interbreed. If you have European or Asian ancestry, you likely carry 1 to 2% Neanderthal DNA. It might not seem like a lot, but it proves that our ancestors were having children with Neanderthals, children who survived and had their own descendants. Some Neanderthal genes persist in us today, influencing our immune systems, skin and hair traits, and even our susceptibility to certain diseases. In a way, Neanderthals didn't completely vanish. They were absorbed into the modern human gene pool, but as a distinct population with their own culture and identity, they didn't survive. Why? Demographics likely played a significant role. Modern human populations seem to have been larger and more dispersed. When two populations compete for the same resources, the larger one usually prevails simply through numbers. Even if individual Neanderthals were as capable as individual modern humans, being outnumbered 10 to 1 would eventually lead to being overwhelmed. Modern humans also appear to have had certain technological advantages. While Neanderthals crafted excellent tools, we developed more diverse and specialized toolkits. We created fine bone needles for sewing-fitted clothing, which offered better insulation. We invented fishing equipment like hooks and harpoons, expanding our food sources. We produced more prolific art and ornaments, possibly indicating more complex social structures or better communication systems. And our trade networks were wider. We find materials at modern human sites that originated hundreds of kilometers away, demonstrating extensive exchange of goods. Neanderthal trade networks were more localized. Trade isn't just about material goods, it's about the exchange of information and the building of social connections. Wider networks mean more people sharing ideas and innovations, which accelerates cultural evolution and adaptation. Some researchers speculate that modern humans might have possessed slightly better language abilities, enabling more complex planning and coordination. Or perhaps our social structures were more effective at resource acquisition or raising children. These are subtle differences that might not be immediately apparent in archaeological remains, but over generations they could compound into significant advantages. Climate, too, might have played a role. The late Ice Age was characterized by incredibly unstable climatic conditions, with rapid shifts between cold and warm periods. Perhaps Neanderthals, who were specialized for cold, stable environments, struggled more with these rapid fluctuations. Modern humans, originating from Africa, which had its own climate variability, might have been more adaptable to changing conditions. But this remains speculative. What's clear is that by 40,000 years ago, Neanderthals were gone, and modern humans were the only human species left in Europe. And we were spreading everywhere, adapting to every environment Earth had to offer. By the end of the last glacial period, humans had reached every continent except Antarctica, having survived the most extreme phase of the 100,000-year cycle. We developed an impressive array of technologies during the late Ice Age. Projectile weapons were a game-changer. Early humans used thrusting spears which required getting close to prey, a dangerous proposition when hunting mammoths. Then came the atlatl, a spear thrower that acted as a lever arm, dramatically increasing throwing range and power. Suddenly, we could attack from tens of meters away, a much safer approach. Later, Probably between 20,000 and 30,000 years ago, in some regions, we invented the bow and arrow. This was huge. Arrows are faster and more accurate than atlatl darts. We could carry more ammunition and hunt smaller, faster animals more effectively. The bow might be one of the most important technological innovations in human history. It fundamentally changed how we could acquire food and defend ourselves. Hunting strategies also became more sophisticated. There's evidence of drive hunting, where groups would herd animals toward cliffs or into constructed traps. Sites with hundreds of bison or horses driven off cliffs and butchered. This required significant coordination among large groups of people. You needed scouts, drivers, people positioned at the cliff to finish off injured animals, butchers, all working together with precise timing. It's complex social behavior that demands communication and planning. Fishing also became important. Humans developed harpoons, fish hooks made from bone, and nets, opening up aquatic resources as a vital food source. The Ice Age wasn't just about survival, it was a canvas for the human spirit. I'm often struck by the stunning artwork they created. Cave paintings like those at Lascaux and Chauvet in France aren't crude drawings. They're sophisticated, dynamic images of animals rendered with incredible skill and accuracy. I find myself wondering about the lives of these people, the challenges they faced, and the ingenuity they displayed. One of the most significant changes during this period was how they secured food. Fishing became a major food source, especially in coastal and riverine areas. It was a relatively low-risk activity compared to hunting mammoths. Coastal sites reveal intensive exploitation of fish and shellfish, with enormous shell middens representing thousands upon thousands of meals. Clothing technology also improved dramatically. Bone needles, appearing around 40,000 years ago, were used for sewing fitted clothing with sleeves and clothes. If you've ever tried staying warm by just wrapping animal hides around yourself, you know it's not very effective. Fitted clothing is far better at trapping body heat. This technology likely allowed humans to survive in even colder regions and remain active during winter instead of just hunkering down. Shelter evolved as well. In regions with scarce wood, people built structures using mammoth bones and tusks as frameworks, covered with hides. These mammoth bone houses have been found in Ukraine and Russia. Some use bones from dozens of individual mammoths, representing thousands of kilograms of material. These were substantial dwellings, not temporary camps. People were investing serious effort into creating comfortable, long-term living spaces. And then there's the art. The artists used the natural contours of cave walls to create three-dimensional effects. They mixed pigments to achieve different colors and understood techniques like shading and perspective. Some paintings even show animals in motion, running or fighting, capturing movement in a static image. It wasn't just cave paintings either. People carved figurines from ivory, bone, and stone. The Venus figurines, stylized female forms found across Europe, date to this period. Some have elaborate details like hairstyles or clothing carved into them. People even made musical instruments, flutes carved from bird bones or mammoth ivory. They created elaborate burials with grave goods, including thousands of ivory beads sewn onto clothing. One burial of children at Sunir in Russia included so many beads that researchers estimated it would have taken thousands of hours to make them. These people valued symbolic expression enough to invest enormous time and effort into it. Why did humans create art? Probably for many reasons. Some cave art might have been connected to hunting magic or spiritual rituals. Some figurines might have been religious or fertility symbols. Some art was probably just for aesthetic plea or social bonding. The point is, Ice Age humans weren't just focused on survival. They had rich inner lives, symbolic thinking, spiritual beliefs, and cultural traditions. They were fully modern mentally and behaviorally, even though they lived in conditions we'd find incredibly harsh. Human populations during the Ice Age weren't huge by modern standards. Estimates suggest maybe just a few million people worldwide, but those people had spread across most habitable regions. They'd reached Australia by at least 65,000 years ago, crossing significant water gaps even during low sea levels. They'd spread throughout Asia and Europe, and critically, they'd made it to the Americas. The populating of the Americas is fascinating. During peak glaciation, when sea levels were low, the Bering Land Bridge connected Asia and North America. But this wasn't just a narrow strip. Beringia was a vast region, probably thousands of kilometers wide, with its own ecosystems. Humans crossed it, probably following game animals, entering a continent with no previous human population and megafauna that had never encountered human hunters. The timing is still debated. The oldest widely accepted sites in the Americas date to about 15 to 16,000 years ago. But there are controversial sites that might be older, suggesting people could have arrived as early as 20 to 30,000 years ago. Either way, once humans were in the Americas, they spread incredibly fast. Within just a few thousand years, there's evidence of human presence from Alaska to the southern tip of South America. That's an incredible migration speed. And remember, the American megafauna went extinct shortly after humans arrived. Mammoths, mastodons, giant ground sloths, horses, camels, all gone within a few thousand years of human appearance. The timing suggests humans played a major role. The Clovis people, with their distinctive spear points and apparent focus on hunting mammoths, have been particularly implicated. But it's complicated. Climate was changing rapidly at the same time. It's probably both factors working together. By the time the Holocene began 11,700 years ago, humans were the dominant large animal on multiple continents. We'd outlasted Neanderthals and other human species. We'd survived the wild climate swings of deglaciation. We'd adapted to every environment from tropical rainforest to Arctic tundra. And we developed incredibly diverse cultures and technologies. Despite being one species genetically, humans showed cultural diversity that no other species has ever matched. This set the stage for what came next, the development of agriculture and the rise of civilization. But that's a different chapter in the story. The point is, the Ice Age and its 100,000-year cycle was the crucible that forged modern human behavior. The technological innovations, the social structures, the symbolic thinking, all developed or were refined during the harsh conditions of glacial cycles. We are, in a very real sense, products of the Ice Age. Our success as a species was built on adaptations to a frozen world, and now that world is gone, melted away as the cycle shifted to its warm phase. The question is, I sometimes wonder if we're truly adapted to the world we inhabit now, or if we're still carrying the weight of an ice age that ended millennia ago. That 100,000-year cycle has definitely shifted. The ice has melted, the megafauna are mostly gone, and we humans now dwell in a world unrecognizable to our ancestors who lived hundreds of thousands of years before us. Welcome to the Holocene, our current interglacial period, a time when everything changed for human societies. Around 11,700 years ago, the Younger Dryas cold snap finally released its grip. Temperatures rose rapidly, then stabilized into conditions remarkably similar to those we experience today. The climate became warmer and wetter than it had been during the glacial period. Forests exploded outwards, carpeting areas that had been cold grasslands and tundra. Sea levels continued their relentless rise as the last of the major ice sheets melted, flooding coastlines and shaping the geography we recognize. It was a dramatic transformation, and a relatively fast one, all things considered. For humans, who had lived as hunter-gatherers for so long, this new world presented both opportunities and challenges. Warmer temperatures meant longer growing seasons, more diverse vegetation, and a more predictable climate. But the megafauna they had hunted for generations were disappearing. Those massive herds of mammoth, bison, and horses, which had been reliable food sources, were gone or going extinct. Humans had to adapt their subsistence strategies quickly or face dire consequences. In some regions, people turned heavily to fishing and gathering shellfish. Coastal sites from this period are littered with enormous shell middens and fish-bone deposits. The ocean, now stable and productive, provided a reliable source of food. In other regions, people focused more on smaller game like deer, rabbits, and birds, supplemented with gathered nuts, seeds, roots, and berries. But these resources require different hunting techniques than megafauna hunting. You can't drive deer off cliffs effectively. You need different tools, different strategies. But in a few special regions, something revolutionary happened. People started deliberately planting and cultivating wild plants. This was the beginning of agriculture, and it changed everything about human society. The first clear evidence of agriculture appears in the Fertile Crescent of the Middle East around 11 to 10,000 years ago. People started cultivating wheat and barley, domesticating sheep and goats. In China, rice and millet cultivation began around 9,000 years ago. In Mesoamerica, maize was domesticated around the same time in multiple regions independently. Within just a few thousand years of each other, humans invented farming. Why did agriculture develop when it did? That's a question that has been debated for ages. One theory points to population pres. During the Ice Age, human populations were kept relatively small by harsh conditions and limited food resources. But as the Holocene began and conditions improved, populations may have grown to the point where hunting and gathering simply couldn't support everyone. Agriculture produces more calories per unit of land than hunting and gathering, so it can support higher population densities. If your population outgrows your hunting territory, you either starve, migrate, or innovate. Some groups chose innovation. Another theory emphasizes climate stability. Agriculture requires planning for the future. You plant seeds, and wait months for harvest. This only makes sense if you can reasonably predict that conditions will remain suitable for plant growth. During the wildly fluctuating climate of the late Ice Age, with events like the Younger Dryas, that wasn't a safe bet. But during the Holocene, the climate became more stable and predictable. You could plant in spring and be reasonably confident that summer would come and your crops would mature. This stability made agriculture viable in a way it hadn't been before. There's also a theory that the Younger Dryas specifically triggered agriculture in the Middle East. The idea is that hunter-gatherers in the Fertile Crescent had developed semi-sedentary lifestyles during the warm period before the Younger Dryas, living in villages and intensively harvesting wild grains. Then the Younger Dryas hit, and those wild grains became less productive. To maintain their lifestyles and avoid starvation, people started actively cultivating the grains, selecting for varieties that produced more food. When the Younger Dryas ended, they were already farming and simply continued. Whatever the initial trigger, agriculture spread rapidly once it started, and it came with a massive package of changes to human society. You can't be nomadic and farm effectively. You need to stay in one place to tend crops and protect them from animals and thieves. So agriculture led to permanent settlements, villages that grew into towns and, eventually, cities. These settlements required new forms of social organization. Who controls the land? How do you store surplus food? How do you defend your settlement? How do you resolve disputes? Agriculture also changed human diets dramatically, and not always for the better. Hunter-gatherers typically had diverse diets with lots of protein and varied nutrients from many plant and animal sources. Early farmers ate mostly carbohydrates from a few grain crops, supplemented with whatever else they could grow or gather. Skeletons from early agricultural societies show signs of nutritional stress compared to hunter-gatherers, more cavities from all the starchy foods, shorter average stature, and diseases associated with dietary deficiencies. Agriculture allowed population growth, but individual health often declined. Disease became a much bigger problem once humans started living in permanent settlements. When you're nomadic and moving frequently, your waste gets left behind, and diseases don't have time to build up. But in permanent villages, the rise of agriculture is a story of triumph and tragedy all rolled into one. It's easy to forget that the seeds of our modern epidemics were sown in those early fields. High population densities, waste accumulation, contaminated water, and our close contact with domestic animals created perfect conditions for infectious diseases to thrive. Many of the diseases that plague us today, measles, smallpox, tuberculosis, influenza, they all originated in domestic animals. They jumped to us humans when we started living in such close quarters with our livestock. Farming, in a way, made us more vulnerable. But agriculture had one overwhelming advantage. It could support far more people per unit of land. I find this fact so striking. A square kilometer of wheat fields can feed dozens, even hundreds of people. That same area of wild land might only support a handful of hunter-gatherers. This meant agricultural societies could grow much larger. More people meant more workers, more soldiers, more inventors, more of everything. And when agricultural societies came into contact with hunter-gatherer societies, the farmers usually won, simply through sheer numbers, even if individual hunter-gatherers were healthier and better warriors. Over a few thousand years, agriculture spread across most of the world where the climate allowed it. Sometimes this happened through migration, with farming peoples displacing or absorbing hunter-gatherers. Other times, hunter-gatherers adopted farming from their agricultural neighbors. Either way, most humans transitioned from mobile hunting and gathering to sedentary farming. This, in turn, set the stage for the rise of complex civilizations. Permanent settlements grew into cities, and these cities required food from the surrounding agricultural areas, leading to the development of trade networks. Trade required record-keeping, which led to the invention of writing in multiple regions independently. Complex societies developed hierarchies, with rulers, priests, craftspeople, farmers, and even slaves forming different social classes. Organized religion became more prominent, with monumental architecture like temples and pyramids built to honor gods or rulers. Specialized occupations emerged as some people focused full-time on pottery, metalworking, weaving, or administration instead of food production. The first civilizations emerged in river valleys, where agriculture was particularly productive: Mesopotamia between the Tigris and Euphrates, Egypt along the Nile, the Indus Valley in South Asia, the Yellow River in China. These civilizations developed writing, mathematics, astronomy, metallurgy, all the hallmarks of complex society. And all of this happened within just a few thousand years of the Ice Age ending. It's an incredibly rapid transformation from small, mobile, hunter-gatherer bands to cities with tens of thousands of people. But here's something else important to remember. While these civilizations were rising, there were still hunter-gatherer societies living successfully in other parts of the world. Australia's Aboriginal peoples, for instance, maintained their hunter-gatherer lifestyles for tens of thousands of years after agriculture was invented elsewhere. In the Americas, many groups remained hunter-gatherers, even while others developed agriculture and built cities. In Africa, groups like the Sand People hunted and gathered successfully until very recently. Some still do. Agriculture wasn't inevitable, nor was it universally adopted. It was one strategy among many, one that happened to be very successful at supporting large populations and complex societies, but not the only viable way to live. The ecological consequences of this Holocene transition were profound. It wasn't just about the megafauna extinctions. Forests expanded dramatically, changing countless ecosystems. Species adapted to open grasslands had to move, adapt, or go extinct. Cold-adapted species retreated northward or to higher elevations, while warm-adapted species expanded their ranges. The distribution of species across the planet shifted massively within just a few thousand years. And humans were increasingly shaping these ecosystems, often in ways we didn't fully appreciate until recently. Indigenous peoples around the world used fire as a landscape management tool, burning regularly to maintain open areas that attracted game animals or promoted the growth of useful plants. This burning had huge effects on vegetation patterns. What we think of as natural, pristine ecosystems are often actually anthropogenic, shaped by thousands of years of human fire management. In Australia, Aboriginal burning transformed large areas from dense forest to open woodland and grassland. In North America, Native American burning maintained vast prairies and savannas that might otherwise have been forested. When Europeans arrived and disrupted these burning practices, ecosystems often shifted dramatically. Forests grew in where they hadn't been for millennia. Fire-adapted species declined, while fire-sensitive species increased. The wilderness the Europeans saw wasn't pristine nature. It was often the result of thousands of years of active human management. The extinction of the megafauna also had cascading ecological effects that we're still trying to fully understand. Mega-herbivores like mammoths weren't just eating plants. They were ecosystem engineers. They knocked down trees, maintained open areas, distributed nutrients through their dung, and created trails and wallows. When they disappeared, these functions disappeared too. Some scientists think forests expanded after the Ice Age partly because there were no longer giant herbivores suppressing tree growth. There's even a hypothesis that megafauna extinction contributed to climate change. Large herbivores produce a lot of methane, a potent greenhouse gas, from their digestive systems. When megafauna populations crashed, methane emissions might have decreased significantly. And the transformation from open grasslands to forests changed the reflectivity of the land surface, affecting how much solar energy was absorbed versus reflected. The loss of the megafauna. It wasn't just loss of food for early humans. It was a loss of materials. Mammoth ivory, for example, was used for tools, for art, even for construction. Their hides became clothing and shelter. Bones? They were used for everything from needles to the frameworks of dwellings. The disappearance of these massive creatures forced humans to find substitutes, and I suspect that this drove a wave of technological innovations. In a way, the extinction of the megafauna might have accelerated the transition to agriculture in some regions. If your primary food source vanishes and you can't find adequate replacements by hunting smaller game, you either starve or you find a new way to subsist. Agriculture became that new strategy. The extinctions that ended the Ice Age world might have inadvertently pushed humans toward lifestyles that would ultimately create modern civilization. The Holocene, the epoch we're in now, has been unusually stable compared to the dramatic climate fluctuations of the Pleistocene. There have been variations, warm periods and cold periods, droughts and floods, but nothing like the dramatic swings of the Ice Age with its rapid warming and cooling events. This stability, I believe, is what allowed civilizations to develop. It's difficult to build cities and plan for agriculture when the climate might flip dramatically within a single generation. But the Holocene stability allowed humans to make long-term plans and investments, building irrigation systems and monumental architecture that took decades, even centuries, to complete. Of course, different parts of the world experienced the Holocene differently. The Sahara Desert, now a vast empty wasteland, was actually green and wet during the early Holocene. From about 11,000 to 5,000 years ago, increased monsoon activity brought more rain to North Africa. Rivers flowed through what is now desert. Lakes filled valleys. Vegetation covered areas that are now bare sand. People lived throughout the region, herding cattle and developing agriculture. Rock art from this period shows hippos, giraffes, elephants, animals that now seem impossibly out of place. But then, around 5,000 years ago, the African monsoons weakened, and the Sahara dried out relatively rapidly. Within just a few centuries, the Green Sahara became the desert we know today. This desertification forced populations to migrate, many moving to the Nile Valley, where water remained available. Some historians believe this migration and concentration along the Nile contributed to the development of ancient Egyptian civilization. Climate change, driving human migration, driving civilization development, all interconnected. Similar stories played out elsewhere. The Middle East was relatively wet in the early Holocene, supporting agriculture and early civilizations. But droughts have repeatedly stressed or collapsed civilizations there. In Mesoamerica, droughts have been linked to the collapse of Maya civilization. In the American Southwest, extended droughts forced the abandonment of settlements like Mesa Verde. Climate variability during the Holocene has been a constant factor shaping human history, even though the swings were mild compared to the Ice Age. And here we are now, roughly 11,700 years into the current interglacial period. Based on past interglacials, we should eventually slide back into glacial conditions at some point. Different models give different predictions. Some suggest we have thousands of years before the next glaciation begins. Others think tens of thousands of years. The orbital cycles are complex, and their effects don't always line up predictably. But there's a massive wild card now. Human activity is affecting global climate on a scale that might override the natural cycles entirely. We've increased atmospheric carbon dioxide from the natural interglacial level of about 280 parts per million to over 420 parts per million. That's a 50% increase in just a couple of centuries. The ice core records going back 800,000 years show nothing like this. We're in completely uncharted territory. And this brings us to the big question: what happens next? It's here where things get really interesting and, honestly, a bit scary. We've spent this whole time talking about how the 100,000-year cycle has controlled Earth's climate for millions of years, creating ice ages and shaping the evolution of life, including humans. But now, for the first time in the history of this cycle, one species has the power to override it, and that species is us. Some scientists think we've already delayed or even canceled the next glaciation. The extra carbon dioxide we've pumped into the atmosphere, warming the planet, making it unlikely that northern hemisphere summers will be cool enough to allow ice sheet formation, even when the orbital cycles shift toward glacial conditions. We might have prevented the next ice age from ever happening. Sounds good, right? Nobody wants kilometers of ice covering Canada and Scandinavia again. But the problem is, we're not just preventing the next ice age. We're warming the planet way beyond normal interglacial conditions. And we're doing it incredibly fast. Let's talk about what we've learned from studying ice age cycles and why it matters right now. First, and most importantly, the climate system has tipping points. It's not linear or gradual. You can push the system for a while and see only small changes, then suddenly cross a threshold and boom, rapid dramatic shifts happen. The Younger Dryas is the perfect example. Gradual warming, then catastrophic freshwater flooding, then abrupt climate reversal within decades. The system flipped states faster than human lifetimes. We're seeing similar threshold behavior today in multiple parts of the climate. Ice sheets don't just melt a little bit at a time. They can remain stable for incredibly long stretches. And then, almost without warning, the melting accelerates rapidly once they pass a certain critical point. I find that idea unsettling, how delicately balanced these systems are. Ocean circulation patterns like the Atlantic meridional overturning circulation can weaken gradually and then potentially shut down with surprising speed. Permafrost, frozen for millennia, can abruptly thaw, releasing greenhouse gases that further amplify the warming. These aren't gentle, smooth changes. These are systems where a small nudge can trigger an enormous reaction. And we're pushing multiple systems toward their tipping points all at once. Arctic sea ice is declining dramatically. The minimum extent in summer has dropped about 40% since we started using satellites to measure it in the 1970s. Some models even suggest we could see ice-free Arctic summers within just a few decades. And, of course, less ice means the ocean absorbs more heat, leading to more warming and even less ice. It's a self-reinforcing cycle. The Greenland ice sheet is losing mass at an accelerating rate, around 250 billion tons per year, according to recent measurements. Greenland holds enough ice to raise global sea levels by about 7 meters if it all melted. While no one expects it to all melt soon, even losing a fraction of it over the coming centuries would have a massive impact on coastlines worldwide. And once major melting begins, those feedback effects I mentioned will make it very difficult to stop. The exposed, darker rock absorbs more heat. Meltwater lubricates the base of the ice, making it flow faster. Warm ocean water gets underneath and melts it from below. These are all positive feedbacks, amplifying the initial change. The West Antarctic ice sheet is particularly concerning because much of it sits on bedrock below sea level. Warm ocean water is already getting underneath it and causing melting. Some scientists believe that major portions of it might be committed to collapse over the coming centuries, even if we were to stop warming today. If that happens, we're looking at 3 to 5 meters of sea level rise. That would completely remake coastlines globally and displace hundreds of millions of people. The carbon cycle is also being disrupted in ways that mirror the Ice Age cycles, but in reverse and at a much faster pace. During glacial periods, carbon dioxide levels dropped to around 180 to 200 parts per million. During interglacial periods, they rose to about 280 to 300 parts per million. This roughly 100 parts per million swing took tens of thousands of years. Driven by natural ocean and vegetation processes, we've increased carbon dioxide by over 140 parts per million in just over a century. We're replicating the entire range of the natural cycle in a tiny fraction of the time, and we're blowing past natural interglacial levels into territory that Earth hasn't seen for millions of years. The last time carbon dioxide levels were this high was probably during the Pleistocene epoch, around 3 million years ago. Back then, temperatures were several degrees warmer than today, sea levels were 15 to 25 meters higher, and the Arctic was forested instead of ice-covered. That's where we're headed if we don't change course. And the rate of change matters just as much as the magnitude. Ecosystems can adapt to gradual changes over thousands of years. Species migrate, evolution selects for new traits, and ecological communities reassemble. But when change happens in decades or centuries, there's simply no time for gradual adaptation. Species either move fast enough or they face extinction. We're already seeing range shifts in thousands of species, plants flowering earlier, animals moving toward the poles or up mountains, and ocean species shifting to cooler waters. Some species are adapting successfully, while others are not, and we're likely headed for another extinction wave. Maybe not as dramatic as the megafauna extinctions, but significant nonetheless. Current extinction rates are already elevated above background levels, and climate change is adding another major stressor on top of habitat loss and pollution. Here's something that I know keeps many scientists up at night. During Ice Age cycles, carbon dioxide changes were a feedback, not a forcing. Orbital variations changed sunlight distribution. This affected temperature. Temperature changes affected ocean chemistry and vegetation, which in turn changed atmospheric carbon dioxide. Carbon dioxide then amplified the temperature changes. It was a feedback loop within the system, responding to external astronomical forcing. But what we're doing is fundamentally different. We're directly forcing carbon dioxide changes by burning fossil fuels. This is direct forcing, not feedback. And all those natural feedbacks that amplified carbon dioxide changes during Ice Age cycles are still operating. They're amplifying the changes we're causing. We're pushing on a system with built-in amplifiers, and we don't fully understand all of them or where the thresholds lie. Permafrost is a huge wild card. There's around 500 billion tons of organic carbon stored in frozen Arctic soils. That's roughly twice as much carbon as is currently in the atmosphere. As the Arctic warms, permafrost thaws, and microbes start decomposing that organic matter, releasing carbon dioxide and methane. It's a classic feedback loop. Warming causes thawing. Thawing releases greenhouse gases, and greenhouse gases cause more warming. How fast this happens is uncertain, but the potential for permafrost to become a major additional carbon source is real and quite frightening. The ocean has absorbed about 90% of the extra heat trapped by greenhouse gases so far, which has slowed atmospheric warming, but at the cost of warming the ocean itself. Warm water holds less dissolved oxygen. We're already seeing expanding dead zones where oxygen levels have dropped too low to support most life. Marine organisms are stressed by warming, acidification from dissolved carbon dioxide, and oxygen loss simultaneously. Coral reefs are being devastated by repeated bleaching events. These ecosystems, which support enormous biodiversity, are collapsing. I find myself thinking about future geologists millions of years from now. What will they make of the sediments they find? These layers that tell the story of our time? They'll see the clear marker of our presence, isotope ratios reflecting massive carbon combustion, extinction signatures, and these strange new materials like plastics and concrete embedded in the earth. They'll recognize that something unprecedented happened during this brief moment. Whether they'll also find evidence that we successfully navigated this crisis, well, that remains to be seen. The Atlantic Meridional Overturning Circulation, or AMO, shows signs of weakening. The data is noisy, and it doesn't go back far enough for my liking, but multiple lines of evidence suggest it might be slowing. If it weakens significantly or even shuts down entirely, it could cause regional cooling in parts of Europe. It's a strange paradox. Even as the globe warms overall, we could see regional cooling in some areas. It's a stark reminder that climate is complicated and often counterintuitive. What do we do with this knowledge? Understanding the 100,000-year cycle teaches us that Earth's climate is exquisitely sensitive to even relatively small changes. The orbital variations that trigger ice ages are in reality tiny changes in seasonal sunlight distribution. Yet, combined with feedback loops, they're enough to tip the system from one state to another. We, on the other hand, are applying forcing that is much larger and much faster than these orbital variations. The response, therefore, will be substantial. The only real questions are how substantial and on what time scale. Climate, as I've come to understand, has momentum. Ice sheets take thousands of years to grow, but they can collapse much faster. Once major melting begins, stopping it becomes incredibly difficult. Ocean circulation changes can be equally hard to reverse. Some of the changes we're causing are essentially irreversible on human time scales. Even if we stopped all emissions tomorrow, temperatures would remain elevated for centuries as the ocean and atmosphere slowly find equilibrium. Sea level would continue rising for centuries, even millennia, as ice sheets keep responding to the warming already in the pipeline. It's an uncomfortable truth to confront. We've probably already committed to significant changes, even with aggressive emission reductions. Some warming, some sea level rise, some ecosystem disruption is already, as they say, baked in. The critical question now is how much more we add. Every bit of additional warming makes things worse. Every tenth of a degree matters when dealing with systems that have these critical tipping points. The paleoclimate record teaches us that rapid climate change is incredibly hard on societies. Climate changes at the end of the Ice Age contributed to the extinction of megafauna and forced major changes in human subsistence. Droughts during the Holocene have toppled civilizations, and those were natural variations, changes over which societies had no control. Now, we're causing changes that are potentially faster and larger than those natural variations. With over 8 billion people to feed and house, many in areas vulnerable to climate change, the implications are staggering. Coastal cities face flooding from sea level rise. Agricultural regions face shifting rainfall patterns and more extreme weather events. Water resources are stressed by changing precipitation and glacial melt. Tropical regions could see temperatures exceeding human survivability thresholds for outdoor work during heat waves. Island nations could literally disappear beneath the waves. The humanitarian implications are enormous, and they are unequally distributed. Those who contributed least to causing climate change are often the most vulnerable to its effects. Understanding the problem, though, is the first and most crucial step toward addressing it. We know more about climate now than ever before. We can see changes happening in real time with satellites and monitoring systems. We can model future scenarios with increasing accuracy. And we have technologies available that could dramatically reduce emissions if deployed at scale. Solar and wind are now cost competitive with fossil fuels in many places. Electric vehicles are becoming mainstream. Energy storage is improving. Carbon capture is being developed, although it's not yet proven at the necessary scale. The challenge, I believe, isn't really technological anymore. It's political, economic, and social. Getting 8 billion people to coordinate on emission reductions, equitably distributing costs and benefits, and navigating competing interests. That's the hard part. Climate change is the ultimate tragedy of the commons. Individual actors benefit from burning fossil fuels, but everyone suffers the consequences. Solving it requires collective action on a scale humanity has never before achieved. I know some people feel despair. The problem can seem too big, changes too slow, obstacles too numerous. I understand that feeling, but humans have navigated existential challenges before. We survived the Ice Age through adaptation and innovation. We transitioned from hunting megafauna to agriculture, fundamentally transforming our relationship with the planet. We've overcome diseases, expanded lifespans, and created technologies that would seem like magic to our ancestors. We're not helpless. We're just facing a problem that requires unprecedented coordination. The 100,000-year cycle will eventually resume, assuming we don't permanently alter it. The orbital mechanics haven't changed. Naturally, Earth would eventually slide back into glacial conditions tens of thousands of years from now, but we're writing a new chapter, one where human activity is a major climate driver, not just a responder. We're affecting the planet on a scale comparable to the astronomical forces that controlled climate for millions of years. No species has ever had this kind of influence. It's both awe-inspiring and terrifying. The cycle reminds us that climate is dynamic, sensitive to forcing, and full of feedbacks and tipping points. It's not a stable, unchanging background. It's an active system responding to inputs. For millions of years, those inputs were natural. Now, we're adding a new input, and the system is responding. We are living through a moment unlike any other in Earth's 4.5 billion-year history. For the first time, a single species understands the global climate system and is simultaneously altering it. It's a strange and daunting thought. We possess knowledge and power that no organism has ever had before. What we choose to do with that power will determine Earth's trajectory for thousands, even millions of years. The Ice Age cycles have shown us that life is resilient. Earth has endured dramatic climate shifts, and life has always found a way to survive, adapt, and even thrive. It survived the asteroid that wiped out the dinosaurs, and it survived countless ice ages. It will survive this, too. The real question is whether human civilization as we know it will thrive, or will we face massive disruptions that could have been avoided with foresight and decisive action. I began this exploration by talking about the mystery of the 100,000-year cycle and how scientists patiently unraveled it. That same scientific community is now sounding the alarm about anthropogenic climate change, using the very same methods that revealed the secrets of the Ice Age cycles. If we trust the science that explained the past, shouldn't we also trust its predictions for the future? It's quite clear that we're pushing the system hard, and we will see significant responses. The window for averting the worst outcomes is closing. The Ice Age taught our ancestors to be adaptable and innovative. That's in our very DNA. We can harness those traits to navigate the challenge we've created, but we need to act collectively and with urgency. The climate system has momentum and time lags. Actions taken today won't show their full effects for decades. But inaction today commits us to changes that will unfold for centuries. Each year of delay makes the eventual response harder and more disruptive. So, where does that leave us? We're 11,700 years into an interglacial period that should eventually come to an end. We're armed with an understanding of how the climate works, and we're actively changing it faster than natural processes typically do. The 100,000-year cycle that shaped human evolution is now being overridden by human activity. We've become a geological force. The only question is whether we use that power wisely or recklessly. The answer will determine what kind of planet future generations inherit, and whether they'll view us as ancestors who rose to the challenge or as a cautionary tale of a species that understood the problem but failed to act. The clock is ticking. The cycle that sustained life for millions of years is still operating in the background. But for the first time, it might not matter, because for the first time, one of the species it created has the power to override it. And what we do with that power in the next few decades will determine not just our future, but the future of countless other species sharing this planet with us. The Ice Age is over. The question is, what comes next? And unlike our ancestors who just had to survive the cycle, we have the power to shape it. That's both an incredible responsibility and an incredible opportunity. Time to see what we do with it